Hi. For many centuries, mathematicians have tried to discover how to solve equations. The cubic and quartic equations, with 3 and 4 as the highest degree of x, were tackled in the 15th and 16th centuries. But it wasn't until the early 19th century that a French mathematician called Évariste Galois proved that it is impossible to find a formula to solve any fifth degree equation. To prove that it is impossible to find a solution is in many ways more difficult than actually finding a solution. To do this, he discovered a totally new branch of mathematics, and this branch of mathematics is now an essential part of the encryption of credit card numbers. He was only 21 years old when he was killed, and he had already made a very significant contribution to mathematics, but that is another story. In this video, we should be looking at attempts to find a formula to solve the cubic equation, an equation in x cubed, and how this led to the discovery of complex numbers. The three main characters in this story are Niccolò Fontana, or Tartaglia, Scipione del Ferro, and Girolamo Cardano, who lived in the 15th and 16th centuries. Niccolò Fontana had an unfortunate childhood. At the age of 12, he was almost killed when French troops invaded his hometown of Brescia in Italy in 1512. Niccolò was slashed across his face with a sabre, which cut his jawbone and severed his palate. His mother tended to his wounds, but he was left with a terrible speech impediment and was then known as Tartaglia, which is the Italian for stutterer. He grew a beard to cover his disfigurement and studied mathematics with a particular emphasis on solving equations. You all know, or at least you should know, the formula for a quadratic equation. In the 16th century, mathematicians believed that it was impossible to solve cubic equations. Tartaglia worked at this with some success, and then found that another Italian, Antonio Fior, was boasting that he had a formula for solving cubic equations. But Antonio's method was not his own. His teacher, Scipione del Ferro, had passed it on as he was dying in 1526. However, del Ferro had only told Fior how to solve one of the 14 different types of cubic equation. Later, Girolamo Cardano heard that an unknown mathematician, Tartaglia, had solved 30 cubic equations with amazing speed, which could only have been done with a formula. In 1539, Cardano gave up looking for a formula for himself and asked Tartaglia whether he, Cardano, could publish his, Tartaglia's, formula in a book. Tartaglia was keen to publish for himself, so he refused. Cardano then enticed Tartaglia to part with his formula by suggesting, falsely, that a wealthy patron was interested in sponsoring him. Eventually, Cardano tricked Tartaglia into giving him the formula and promised not to reveal it to anyone else. Tartaglia passed on his formula in verse. When the cube with the co's beside it equates itself to some other whole number, find two other of which it is the difference. Hereafter you will consider this customarily that their product will always be equal, and so on. Well, that's rather a puzzle in itself. And this was written, if we look down at the bottom, in 1534. If anyone can understand this, then please let me know. Later, Cardano, with a colleague, Annibal della Nave, discovered an old notebook which had belonged to Annibal's father-in-law, who was Scipione del Ferro. In this notebook, they discovered del Ferro's formula, and then, as they were not bound by promises of secrecy to Tartaglia, they published the formula. Tartaglia was not satisfied with the credit given to him by Cardano, and at the same time he also had the misfortune of being beaten to the discovery of a formula for the quartic by a young 18-year-old mathematician. Cardano committed suicide on the 15th of September in 1576. This was apparently to fulfill a prophecy that he had made earlier about when his life would end. Now we come to the formula. We have to have some mathematics somewhere. Well, here is the formula. I'll let you just look at it and enjoy it for a moment or two. We only look at equations like x cubed equals px plus q, which can be written as x cubed minus px minus q equals 0. I will show in a later video that any cubic equation can be written in this form. Okay, now let's see how well it works. I've set up a spreadsheet here with the formula in it and values of p and q, which you can see there. And when p is -1, q is 10, and x is 2. I just want to be able to write quite neatly, so we'll pop in some lines. And we'll make a little table of results. We've got on the thing here that when p is -1, q is 10. This gives us, if we look at the spreadsheet, that x is 2. Well, x cubed minus px minus q is x cubed minus px is plus x minus q is -10. We know that that gives us a factor of x minus 2 because x equals 2 is a root. We know that we must have x squared, and at the far end we must have plus 5. If we look at the fact that there are no x squared terms in the expression, we have minus 2x squared here. So we need plus 2x squared there to get rid of the x squareds. That means we need plus 2x. Check. That gives us plus 5x minus 4x, which is 1x. So that's right. If we look at x squared plus 2x plus 5, b squared is 4, it's 2 squared, and 4ac is 4 times 5 times 1 is 20. b squared is less than 4ac, and so in this instance we have one real root, one root. Okay, let's look at something else. Let's try using p equals -2, and we'll try q equals 33. Okay, that has all been happening in the background. If we refresh the spreadsheet, when p is -2, q is 33, gives us x is 3. So if we carry on with the table, p is -2, q is 33, x is 3. The equation is x cubed minus px minus q. P is -2, so that's x cubed plus 2x minus q is -33. X equals 3 is a root, so x minus 3 is a factor. We must start with x squared. -3, I need plus 11. 11 times -3 is -33. If we look in the middle at the x squared term, we've got -3x squared. We don't want any x squareds, So I need to put plus 3x there. Plus 3x. Once again, if we look at that second expression, b squared is 9, which is less than 4ac, which is 44. So no roots from the second bracket. This has only one root. Well, what happens if we have more than one solution? Don't know if you've got any ideas. Let's suppose that we start off with x is, say, 2. Another idea, x is 1. And a third idea, completely at random, let me choose one, minus 3. Well, if we've got an equation with those roots, we have factors of x minus 2, x minus 1, and x plus 3. That gives us x squared minus 3x. Sorry, I can't. Yes, it is. X squared minus 3x plus 2 times x plus 3. And if we multiply those two together, we get x cubed. Then for the x term, or x squared term, we've got minus 3x squared plus 3x squared. So we haven't got any x squares, that's very lucky. We've got minus 9x plus 2x is minus 7x. And then we've got 3 times 2 is plus 6 at the end. So this is x cubed minus 7x is p equals 7. And q equals minus 6. That then gives us x cubed minus 7x plus 6. So what happens if we do this? Let's have a go. I've got to change p to 7 and q to minus 6. Come back here. Whilst you've been watching that, something's been happening in the background, and no luck. Complete disaster. So when p is 7 and q is minus 6, we have a disaster. But we know that there are 3 roots. So that's not all that satisfactory. Well, perhaps we might try something else. Let's try, well, any ideas? X equals 2. Well, that's the same as last time. We better have something different next. Minus 5. And I'll just put something else down totally at random, 3. That gives us factors of x minus 2, x plus 5, x minus 3. X minus 2, x plus 5, x minus 3. Multiplying that out, first 2 brackets give us x squared plus 3x minus 10, x minus 3, x cubed. Now if we look at the x squared term, we get 3x squared there, minus 3x squared there, so they disappear again, which is rather fortunate. We have minus 9x minus 10x gives us minus 19x, and minus 3 times minus 10 gives us plus 30. So this is x cubed minus px, so p is 19, minus q, so q is minus 30. We know that we've got roots of 2, minus 5, and 3. I didn't put the roots on the previous one, 2, 1, minus 3. Okay, P is 19 and Q is minus 30. Let's go away to the spreadsheet, which I'm afraid you can't follow me, but that's bad luck. P is 19 and Q is minus 30. So that's been happening in the background. Let's refresh the spreadsheet, and it didn't like it again. Another disaster when we have 3 roots again. Well, what's going on? Let's go on down and let's have a look at the formula and see what's happening. The first case we had that it didn't like, we had P was equal to 7 and Q was minus 6. Well, in the formula, we have here a square root sign, this one. There's one in both bits, same thing underneath. Let's look at what we have underneath the square root sign. We've got Q over 2 squared sorry about the pause, Q over 2 squared minus P over 3 squared. Q is 6, so that's 3 over 2 squared. The minus disappears, so we've got 6 over 2 is 3, 3 squared is 9, minus 7 cubed is 343, and 3 cubed is 27. Let's put the 9 over 27, that's 243 over 27. And then minus, won't write, sorry, technical problems while I'm trying to get the pen to write, minus 343 over 27. And that is minus 100 over 27. So that is negative. So under the square root sign, we have something which is negative, and we can't have a square root. This happens with all cases where we have 3 real roots. If we have 3 real roots, the number under the square root sign is negative. There is one little puzzle here. How can you write down 3 roots to guarantee that you won't have an x squared term in your expansion? Well, those of you that have done the further pure in year 11 may remember that for a quadratic equation, the sum of the roots was minus b over a, where b was the coefficient of x. The same sort of thing is true with a cubic, that if you have the sum of the roots of a cubic, that is equal to minus b over a, where a is the coefficient of x cubed, and b, importantly, is the coefficient of x squared. So if the sum of the roots is 0, then the coefficient of x squared must be 0. So you write down 2 and 1. 2 plus 1 is 3. Subtract 3, you get 0. 2 minus 5 is minus 3. Plus 3, you get 0. So it's very easy to write down 3 roots so that you can guarantee to have no x squared term in your expansion. Okay, let's go on now to have a look, if I can get this screen to move, at what happens if we have 2 solutions. If we have 2 solutions, then the graphs will show you that you must have a tangent at the maximum of the x-axis must be a tangent there, or the x-axis must be a tangent at the minimum. If you have the x-axis anywhere else, you will either get one root or three roots. Well, let's take the second case where the x-axis is a tangent at the minimum. And let's try taking some particular values. Let's suppose that our repeated root is x equals 2. Then we have x equals 2 or 2. And from what we've just said, we should all know what the third root is going to be. It's going to have to be minus 4, so that the sum of the roots is 0, and we will have an equation of the right form. Well, if we've got that, then we have x minus 2 is a repeated factor times x plus 4. X squared minus 4x plus 4 times x plus 4. X cubed, we're not expecting to get an x squared. Minus 4x squared plus 4x squared, yes, they do go. Minus 16x plus 4x is minus 12x plus 16. So in this case, we've got P is 12 and Q is minus 16. P is 12, Q is minus 16. So let's go back to the spreadsheet, 12 and minus 16. Okay, let's see what this gives us. P is 12 and Q is minus 16. Okay, everything's been working in the background. Let's refresh this. P is 12, Q is minus 16. This gives us minus 4. We had 2, 2, and minus 4. So the formula, when there are two roots, one of them must be repeated. The formula will only give us the non-repeated root. Okay, let's go down again. So there's this lovely formula, and we've discovered that it doesn't always give us the right answer, or any answer sometimes. If the equation has got only one real solution, then the formula will always give the answer. If the formula's got one repeated solution and a third, or if you like to think of it second, different solution, the formula gives the non-repeated solution. If the equation has three different solutions, the expression under the square root sign is negative. Well, what would you do now if you were looking for the solution, looking for a formula, and you knew there were three solutions and the expression just went wrong? Well, I think I know what you would do. You would give up. And that is exactly what Cardano did. He gave up. At this point, Raphael Bombelli, another Italian mathematician, comes into the picture. He assumed that there was some meaning to the square root of a negative number, and he formed rules to handle these complex numbers, as we now call them, and then he was able to use Cardano's formula to solve cubic equations which had three distinct real roots. He published his book, Algebra, in 1572, in which he explained the arithmetic of complex numbers. There it is. Plus by plus of minus makes plus of minus. Minus by plus of minus makes minus of minus. Plus by minus of minus makes minus of minus, and I'm sure you're all following this with no trouble. For years after this, many mathematicians thought that complex numbers were a waste of time, but others developed the theory of complex numbers. In 1620, Albert Girard suggested that an n-degree equation would have n roots. René Descartes suggested the term imaginary, and that some of the n roots might not be real. Leibniz and Bernoulli used imaginary numbers to aid integration. D'Alembert used them in hydrodynamics. D'Alembert, Euler, and Lagrange tried, incorrectly, to prove the existence of n complex roots for an n-degree equation. This was later proved by Gauss in 1797. Euler used the symbol I for the square root of -1, and Gauss represented complex numbers on a plane, as did a Swiss mathematician Argand in 1806. In 1833, Hamilton expressed complex numbers as a pair, AB, and we now write this as A plus BI. So it took from around 1560 to 1833, a period of about 270 years, for mathematicians to accept fully the idea of complex numbers.